Before we set up and solve systems of equations, I want to talk just a little bit about matrix multiplication. Matrix multiplication is based on something called an inner product. An inner product, by definition, is the multiplication between a row vector and a column vector. The result of that is a scalar, or a single number, and that number is the summation of the products of the respective elements in each one. So if I have a row vector A1 and A2 and multiply that by a column vector B1 and B2, the result is going to be the product of this times this, so A1 times B1 plus this times this, A2 times B2. As a numerical example, if we multiply this row vector 1, 2, 3 times this column vector 4, 5, 6, the result's going to be this times this, or 1 times 4, plus this times this, which is 2 times 5, plus this times this, which is 3 times 6, and the result is 32, which is just a number. When multiplying two matrices, each element of the output array is the inner product of the corresponding row vector in the first array and the column vector in the second matrix. The element in the first row and first column is the inner product of the first row of the first matrix times the first column in the second matrix, which is 1 times 5 plus 2 times 7. The first row second column is going to be the first row times the second column, so 1 times 6 plus 2 times 8. The second row, first column, is 3 times 5 plus 4 times 7, and the second row, second column is the inner product between the second row of the first matrix and the second column of the second. So it's 3 times 6 plus 4 times 8. And the result is 19, 22, 43, and 50. Now, before I talk about solving systems of equations, I want to talk about dividing scalars, or single numbers, which we should be pretty familiar with. If you divide one scalar A by another one B, that's the same as multiplying 1 over B times A. 1 over B is defined as being the inverse of B. The definition is that 1 over B times B is equal to 1 because this cancels with this. Terminology for 1 over B is just B inverse, so B inverse times B is equal to 1. Solving systems of equations requires us to take the inverse of a matrix, which I'll talk about next. So in order to divide by scalars, we had to have the idea of a 1. So something times its inverse was 1. The matrix version of 1 is the identity matrix. The identity matrix has 1s on the main diagonal and 0s off the main diagonal. The main property of an identity matrix is if you multiply a matrix times an identity matrix, you get the original matrix back. So if I have a matrix that's A1, A2, A3, and A4, and multiply that by a 2 by 2 identity matrix, I multiply this row times this column, that's A1 times 1 plus A2 times 0, which just gives me A1. First row, second column is A1 times 0 plus A2 times 1, which is A2. Second row, first column is A3 times 1 plus 0 times A4. And finally, second row, second column is just A4 times 1 plus A3 times 0. And I get the original matrix back. So any matrix multiplied by an identity matrix gives the original matrix back. Now I want to define a matrix inverse. I'm going to define that in much the same way as we defined an inverse of a scalar. The definition is that a matrix A multiplied by its inverse gives the identity matrix back. I can either post-multiply A by A inverse, in which case A inverse shows up after A, or I can pre-multiply A by A inverse, in which case A inverse comes before A in the expression. Either way, the result is an identity matrix. I can use this to solve systems of equations. If I have a set of equations in this form, so for example, A1, A2, A3, A4, a 2 by 2 matrix of numbers, times a vector of variables, x1 and x2, is equal to a column vector of numbers, b1 and b2, and I need to find these, I can pre-multiply both sides of the equation by A inverse. So if I multiply this by A inverse, that gives me I, and I multiply this by A inverse, then I times the vector of x's will just give me my x vector back, and the unknowns will be the product of the inverse of A and the vector b. MATLAB provides a variety of ways to solve these equations. There is an inv command which will explicitly return A inverse. If I take the inverse of A and then multiply it by b, I get x back. A raised to the negative 1 power to MATLAB is the same as this, so I can multiply that by b. And finally, I can use this backslash operator, which looks like division to MATLAB. The b is in the numerator, the a is in the denominator, so this to MATLAB looks like b over a, which is A inverse times b. As an example of writing and solving systems of equations, I'm going to look at this beam. I've got an applied force here of 100 newtons at a 45-degree angle from the positive x-axis. This is a roller. It will support vertical forces only. This is a hinge. It will support both vertical and horizontal forces, but it will not keep this from rotating. So a vertical force here at the roller and both vertical and horizontal forces at this hinge. So let's write the equations governing this system and then we can solve them. So I'm going to call this end A. Fax is horizontal, positive to the right. Fay is vertical, positive up. This is point B. It has only an fby, which I've chosen to be positive up. And then I've decomposed this force into x and y components. Now let's write the equations governing this. So the sum of the forces in the x direction has to be 0 to keep this from moving. So positive to the right, Fax minus 100 times cosine of 45 degrees is equal to 0. Now the sum of the forces in the y direction, with positive being up, is Fay plus Fby minus 100 times sine of 45 degrees is equal to 0. Those two equations will keep this from moving up or sideways. Now I need to make sure that it doesn't rotate around this point. Moments cause a rotation, so the sum of the moments at A is equal to 0, and I'm going to say rotation in this direction is positive. To make something rotate, you not only need a force, but you also need a moment arm. So this 100 sine 45 degrees is going to try to cause this to rotate in the positive direction. So I have a force of 100 times sine of 45 degrees times a moment arm of 8 meters. Fby is going to try to make this rotate in the opposite direction, so minus Fby times its moment arm, which is 5 meters, is equal to 0. So there are 3 equations and 3 unknowns. Next, let's put them in matrix form, and then we'll use MATLAB to solve for the 3 forces. Here are the equations we got on our previous slide. We want to put these in matrix form. Since I have 3 equations and 3 unknowns, the matrix A is going to be a 3 by 3 matrix. These are so I can keep track of my rows and my columns. I have a vector of unknowns here. There's going to be 3 of those, is equal to some right-hand side vector of coefficients. The first thing I need to do is choose what order my unknowns are going to go in this vector x. I'm going to say that their fax is first, fay is second, and fby is third. The order here doesn't matter, but I need to decide on an order and stick to it so that I can fill in the a and the b vectors. This equation is 1 times fax. Fay doesn't show up. I can get rid of that by multiplying it by a 0. And fby doesn't show up. So that's a 0 times fby. And that, if I take the constant over here, is 100. Cosine 45 degrees is 1 over root 2. It's 100 over root 2. If I put this equation in matrix form, I get a 1 times fax, 0 times fay, and 0 times fby is equal to 100 over root 2. I can rearrange the second equation in the same way. This is 1 times fay plus 1 times fby plus 0 times fax, because fax doesn't show up in this equation, is equal to 100 over root 2, because the sine of 45 degrees is also 1 over root 2. So this is 1 times fay, 1 times fby, 0 times fax is 100 over root 2. So if I multiply this row times this column, I get 0 times fax, 1 times fay, 1 times fby is equal to 100 over root 2. The final equation is minus 5 times fby. Fax and fay don't show up in there. And this is equal to 800 times the sine over 45 degrees. Take this to the other side, it's negative, so this is minus 800 over the square root of 2. So now I have a system of equations I can plug into MATLAB and solve for fax, fay, and fby. Okay, the A matrix is A equals open square bracket 1 space 0 space 0 semicolon to go to the next row, 0 space 1 space 1 semicolon space 0 space 0 space negative 5 close square brackets. So there's my A matrix. My B vector is open square bracket 100 divided by the square root of 2 semicolon to go to the next row, 100 divided by the square root of 2 semicolon to go to the next row, and negative 800 divided by the square root of 2. Close square brackets. There's my B vector. I can solve for x is equal to a backslash b, or x is equal to the inverse of a times b. They both give the same thing. These are in the order fax, fay, and fby.